From safer code generation and vulnerable package versions to emergent modularity in giant MoE models and the hidden risks of graph learning, today's papers reveal how modern AI behaves when it leaves the lab and meets the real world. We'll explore why some LLMs keep choosing risky dependencies, how expert routing can create reusable semantic modules, and where graph models break under corruption, imbalance, fairness, and distribution shift. Stay tuned for a tour of AI's most surprising strengths and fragile blind spots. Let's explore the first paper. Correct code, vulnerable dependencies, a large-scale measurement study of LLM-specified library versions. Correct code. Vulnerable dependencies presents the first large-scale measurement study of version-level risk in LLM-generated Python code, evaluating 1.0 models on pintrace, a 1,000-task Stack Overflow benchmark built from 267 third-party libraries and an OSV-backed vulnerability index. The core finding is that version selection is governed by output format, not model quality. Inline prompts trigger version pinning for 26.83%, 95.18% of imports, while explicit requirements, TXT prompts drop to 6.45%, 59.19%. Those pinned versions are often stale and risky, lagging each model's cutoff by 931 months, and they repeatedly converge on the same small set of releases, such as requests equals 2.31.0 and Django equals 6.0.1. Under inline prompting, 36.7%, 55.7% of tasks include at least one version with a known CVE, and 62.75%, 74.51% of vulnerable versions are critical or high severity. 72.27%, 91.37% of those CVEs were already public before the model's cutoff. Compatibility is also poor. Static compatibility falls to 19.7%, 63.2%. Dynamic BigCodeBench pass rates collapse to 6.49%, 48.62%. And installation failure is the dominant cause. A controlled neighboring version substitution experiment shows that 17.19%, 55% of installation failures are fixed by changing only the version, proving the defect lies in version selection rather than code logic. Prompt-level safety instructions barely help, but external version anchoring cuts vulnerability exposure to roughly 10%, 22%, and raises static compatibility to 80.92%, 93.64%, showing that live dependency grounding is the practical mitigation. Let's explore the second paper, EMO Pre-training Mixture of Experts for Emergent Modularity. EMO introduces a pre-training objective for mixture of experts models that makes expert subsets usable as standalone modules without human-defined domain labels. The core idea is document-level routing. For each document, the router selects a shared pool of experts, and every token in that document can only choose among that pool, with a pool size D sampled uniformly from K to NR during training. The authors train a 1B active, 1 4B total parameter model with 128 experts. K equals 8 active experts per token on 1T tokens from the OMO corpus, using global load balancing rather than micro-batch load balancing to stabilize training. As a full model, EMO matches a standard MOE on MC9, Gen5, MMLU, MMLU Pro, and GS Machtka. Its key result is selective expert use. On domain-grouped MMLU and MMLU Pro, retaining only 25% of experts causes about a 1% absolute drop, and retaining 12.5% causes about a 3% drop, while a standard MOE degrades by roughly 10% and 15% under the same constraints. EMO also outperforms memory-matched models trained from scratch, such as an 8 expert-dense baseline, and remains robust under both router-based selection and easy EP pruning. Routing analyses show a qualitative shift from low-level syntactic specialization in standard MOEs to semantic specialization in EMO, with clusters aligned to domains like math, code, biomedical research, and politics. Let's explore the third paper on the safety of graph representation learning. On the safety of graph representation learning introduces GRL safety, a benchmark that tests 12 graph representation methods across 25 text-attributed datasets under 5 deployment stress axes: corruption, robustness, out of distribution, generalization, class imbalance, fairness, and interpretation. The evaluative models span deep walk, Node2Vec, GCN, GAT, GraphSage, BGRL, GraphMay, and foundation-era systems including GFT, GIT, Unigraph2, OFA, and LL-Laga, all compared under standardized splits and shared sentence-BERT 768 dimensional text features, while preserving each method's native adaptation pipeline. The main result is that safety is not a property of model family alone. Under 50% edge deletion, DeepWalk and Node2Vec lose about 9.6 to 9.8 accuracy points, while supervised and self-supervised GNNs typically drop by only 1 to 3 points. On OOD shifts, the best method changes by regime, with GraphMay showing the smallest degree shift drop at 6.75 points, OFA performing best on the RxIve temporal split with a 9.61 point decline, and BGRL or OFA leading different inductive knowledge graph settings. For imbalance ratio 10, minority class recall can collapse to near zero for topology-only embeddings despite strong majority recall, exposing a major minor trade-off. Fairness results show degree position disparity as high as plus 20.89 points on WikiCS for Node2Vec, while Laga can even reverse the gap on some graphs. In interpretation, GFT achieves the strongest edge saliency fidelity, with a cross-dataset average characterization score lift of 31.3 over random baselines, nearly tripling many competitors. That's a wrap on today's AI paper highlights. Thanks for watching.